Okay, so you've all been to Regev's lecture just 2 hours ago, and hopefully you all agree now that confidence intervals are important and are hard to construct. So I'm going to talk about how to do it quickly. So there's a nice trick that Regev uses to do it for heritability, but that's only for heritability, and I'm going to talk about more general tricks that work in any scenario, or at least most scenarios. So I'll start with a recap of what Regev did, because I'm sure you all forgot 2 hours is a long time. So we have an estimator for some quantity theta, for example, heritability, and we say that the heritability is 0.8, which sounds like a lot, but if we build confidence intervals, they may come out like this, 0.23 to 1. Which isn't as informative, and I'm sure you all would like to know that before you make a decision based on an estimate of something. You really what is the size of the uncertainty, how big the uncertainty is. And building confidence intervals may be difficult if in cases when normality does not hold. So what is test inversion? That's the method that Regev uses and the one that I work on. Basically, you have a distribution function, theta, and you have an estimator for it, theta hat, and you want to find the endpoint, theta u, which gives a 95% confidence interval. And what the test inversion means is that if we take theta u and plug it into our parametric model, and then draw a sample from this model and estimate our quantity, the probability of being less than the original estimate is alpha, which makes sense. We take theta, we replace it by something bigger, and we accept our estimates to be bigger now. How much bigger? Exactly that much. Now, how can we use this property to find theta up? So the straightforward way, just like Regev described, is to choose a set of points on a grid and simulate the data set on each, to simulate many data sets from each point. And then we can calculate the sample quantiles and we can invert them, interpolate them and invert them. So it looks like this. You choose a grid of points, you plug each one to the parametric model. You sample many samples from for each point, and then you get a lot of estimates for each true value of theta. And you can plot them, calculate the sample quantiles, just straightforward sample quantile for each point you sampled, and then interpolate them. And then you want to invert them. So say our original estimate was 1. The upper endpoint is going to be here, this x value here. So we can't really see it, but that's 2 point something, 2.6 maybe. It's just a toy example.
Is the bottom of the slide missing?
Yeah, I don't know why. Oh, here it is. Okay. The screen is not big enough to fit the slide. Okay. So that's how you invert sample quantiles. But the problem is that it can take a very long time. Simulations, we work with a lot of data, and simulation can take a long time. If you have 50,000 or 500,000 or 1 million SNPs, and you have kind of a correlation matrix between them, you need to draw a lot of samples from that with that correlation structure, and it can get pretty computationally heavy, and no one wants to wait for a month while these computers build the confidence intervals. So what can you do? You can use quantile regression. I don't know if any of you heard about quantile regression, but it's very much like regular least square regression. Again, we have this. Okay. So instead of modeling the conditional mean, we model the conditional quantile, and we follow a pretty straightforward optimization procedure to find the best fitting line. So again, that's okay. So that's the least square regression line, and that's the quantile regression line. That's pretty intuitive, and I hope it's clear now that instead of doing this, sampling many points, calculating the sample quantiles, interpolating them, you can sample just 1 point and calculate the quantile regression line. And then you can invert it the same way. So you go to 1, you find where it meets your line, and that's your upper endpoint. So that's an example on mutation rate estimator. What's an estimator in a coalescence model? We took an estimate for mutation rate in humans. That's 10 to the minus 8. That's the estimate we used. And we simulated many samples at each of those points. And according to the many samples, we built the solid lines. So the solid red line and the solid blue line. Those are the acceptance. This is the acceptance region. And then the dashed lines are based on the quantile regression with 1 sample on each point. So that's a factor of 1,000 samples. That's much less. It will take much less time. And as you can see, the error from using quantile regression seems to be quite low. So the procedure seems to be quite accurate. And those are some mean squared errors for different methods to do the same thing. Quantile regression is what I just described, and that's the best, the lowest MSE. And Robbins-Monroe and binary Robbins-Monroe are 2 procedures for stochastic search, that instead of sampling at each point and using all of this information to find the best fitting line, they do a search for the endpoint that moves according to the last point sample. So as you can see, quantile regression does better than the other methods. So to conclude, if you need to build a bootstrap confidence interval, but you can't because it takes too long, you can just choose a grid of points for the parameter value, sample 1 bootstrap sample at each point. So simulate 1 data set for each one of them. Use quantile regression to find the conditional to quantile and then invert it. So that's it for quantile regression. I didn't want to go into the math because I didn't think it can fit in 15 minutes. But there are some more interesting questions regarding how to do it right. So for example, what is the best sampling scheme? How to choose the points to achieve minimal variance of the estimator? And we have some nice results for that. What happens if the conditional quantile is not linear, which can happen when the variance of the estimator changes with the mean. So there are some solutions here as well. Can we combine the 2 methods of stochastic search, Robbins-Monroe procedure, with quantile regression to achieve better results? And how can we measure the additional uncertainty from the approximation? Because when you do a quantile regression, or when you do a stochastic search, or even when you use sample quantiles, you have additional uncertainty because you can't really be sure what the correct conditional quantile is. So how can you measure that and add it to your analysis? And that's it. That's what I do.